Yeah, okay. Yeah, okay. It's also, so welcome on my behalf. So first off, the title is a bit misleading. So this isn't really about reinforcement learning for games at Supercell, but mostly about Moco, which is the newest Supercell game uh, here. But the other reinforcement learning use cases for other games are kind of similar, so maybe it's kind of general enough. Um, Yeah, a little bit about me. I'm Heikki Arponen, math PhD from '09, University of Helsinki, so a local boy. About 12 years in industry, machine learning, deep learning, mostly PyTorch, vision language models. My maybe like first public project was with Tiano from 2014, derp RNN, because deep RNN was taken, so kind of like a super funny joke. So far I've been about 20 months at Supercell doing reinforcement learning for Moco, and that's actually my first like real reinforcement learning project. So I'm not really like an expert on reinforcement learning, but maybe getting there. And I didn't have to start from scratch, so there was already a functional reinforcement learning thing working specifically a working AI simulator. Uh, okay, get into that later. So what is Moco? So Moco is a multiplayer PvE game where the objective is to hunt monsters, collect XP and loot with friends or random people. So I'm just kind of skipping forward. This is the initial thing, and then you get different kinds of gears, and then you go out and fight monsters. And so it's a PvE game, so all players play on the same side against NPC monsters. Um, yeah, and then the motivation. Why reinforcement learning? So first off, reinforcement learning. So imagine if you're training a dog, you don't explain the rules to the dog, but you reward correct behavior. And the current use case for the bots in Moco is game balancing. So the bots are not in the game. You're not going to play against these reinforcement learning bots in the game. The game bots in the game are these kind of classic rule-based bots currently, so far at least. The idea is massive scale testing. So we train thousands of these AI bots to play the game, to test new gear, new content, new features, overall game balancing, and also exploit discovery. So try to find unintended strategies that kind of break the gameplay. And speed is kind of important. We need the results fast, like within hours maybe, or at the next day at the latest. So the game designers can kind of iterate on that. And since Mogo is a new game, using gameplay data or player data was kind of impossible. And that's fine. Reinforcement learning works. Yeah. Yeah, and what happens in practice for typically, at least the idea was that there would be a content update like maybe every few months. And before every release, we do balancing runs for maybe 1 or 2 weeks. Get results, or the designers make a new version of the game. Then we let the bots train, get results on the next day, adjust levels and enemy stats and so on, and then do it again until convergence. And then what happens in practice? Oh no, wrong video. I don't know. I'm trying to run this one first. So this is a typical fight. Sorry, no audio. This is a gameplay replay. So the replay actions are stored and then it's replayed in the game client. So they fight this boss and dodge the danger tiles and so on. In general, they're kind of Maybe not sure if they're superhuman, but at least like really, really good. Okay, they can take care of that one. And then example of an exploit. Bam, 1 second and it's complete. That was kind of unintentional. So just for the record, so this is a replay, so it kind of repeats the last action at about 1 second. So basically, if you have the exact right combination of gears, then you try many times, and if you get lucky, you get this kind of chain of critical hits, and you can complete the dungeon in 1 second, which is not intentional. So then game designers adjusted the game so that this doesn't happen again. Yeah, and then to the actual technical details. So the AI simulator. So we're using this kind of a terminology from like a simulator simulating like a real thing, like a drone or whatever. It's not really a simulator, but anyway, that's the kind of jargon for this. So the AI simulator is a headless game client. So there's no rendering. That would be computational and kind of heavy. So it's a separate multi-threaded parallel build of the game client, rendering disabled. It enables like an order of 1,000 parallel environments per GPU machine where we actually train the models. And the parallelism is kind of essential for scaling the learning. Very important. And we have full game access because, well, clearly we have Supercell games and we have the game code in C++. So we can get the observations and define the observations and rewards directly. And since we're working in Python, we have a Python bindings, connects the C++ written simulator to whatever Python code you want to run. Some pros and cons. The good thing is that we can fully control the observations and the rewards. It's massively parallel. And yeah, we had direct access to the actual game state. There are some challenges like you have to work directly with the game's C++ code base, which can be a bit of a challenge, especially to me. I suck at C++. I wouldn't be able to do this stuff alone. And especially can be hassle for new games where there's like lots of changes all the time happening. And the AI simulator is kind of at the bottom of the dependency chain. So there's the game engine, then the actual game, and then the AI simulator shit flows downhill. Kind of a challenge. And yeah, the training framework. Oops. Yeah, so once you have a working AI simulator, it's just pip install AI simulator and import it into Python code. Then, well, this is pseudocode only, so it's not literally quite that simple. But you feed in an action to the AI simulator, you get an observation and a reward. Then you feed the observation into the agent, you get the next action. And we have some examples of what the observations are. So there's a crop of the game tile map around the player. Kind of simple. And then a bunch of unstructured information. Player, whatever, categorical and continuous variables and team, enemy, all kinds of characters and so on. And the agent output is just the softmax over the action. So this is the move action, then there's the button action. And what we are doing, this is basically a small in-house reinforcement learning library. Everybody's kind of using the same code or very similar code.
What is the camera view again, the numbers?
What happened? Sorry? Oh, yeah. Okay.
Well, sorry. What is the camera view numbers again? I missed that part.
Sorry, just a sec. If I can get that. No, I can't actually see the presentation. What happened? present a view and question. Sorry, and the question was, what was the camera view? Oh, it's just it's 21 by 21 crop, so the numbers don't mean anything. Sorry about the bad plot. My matplotlib skills are not that good, maybe. Yeah, so basically the agent is there in the middle, and this is a hallway here. These are walls, and then these are, I guess, like different shaped wall tiles. And the reward is just a number, real number. Yeah, so small in-house library. Considering also RLib, but not sure there are some trade-offs. And in any case, the actual reinforcement learning code is still kind of like a smallish part of the total Python code anyway. There's like lots of other stuff to worry about, so it's not that important maybe. Yeah, and then about the model. So model architecture is a recurrent network. So first stage here, okay, so there's the observation that goes to a feature extractor, not part of the model. Then an encoder, fully connected PyTorch module. What the hell is going on? It's changing shape. Okay, but anyway. Then it outputs a vector, goes into an RNN. I'm using GRU at the moment. So that RNN takes in the encoder vector and the previous RNN state. Then the RNN state is used for a policy head that will output a logit for a softmax, which is the action distribution. Well, there are two actually separate for move and the buttons. And also it's the RNN state is also used for the value head. Value head will try to predict the future rewards or returns. And okay, that's detached from the rest of the network. It runs on experiments that this seem to lead to more stable training, so that the value head gradients don't interfere with the rest of the model training. And the algorithm we're using, I think everybody's probably using PPO, so policy gradient method, where we clip the gradients if the policy deviates too much from the old policy that's collected during the rollout. So basically, there's two phases. The rollout phase, we run the game, collect state action pairs, and store also the old policy values here. And then the advantage is computed from the rewards. And basically what it says is that the thing A I did at state S, did it lead to a positive or negative outcome? If it led to a positive outcome, then the advantage is positive, and vice versa. So for example, so policy gradient is not like super rigorous, but it's kind of heuristically nice heuristic. It's kind of like if I was at a party S and I told a bad joke A, people were angry at me. A would be negative. I would be like, oh no, I'm not gonna tell that bad joke again. And the gradient direction here would be negative. The policy probability that I will tell that joke again at that state will go down a bit. And vice versa, if I had did a great presentation A at conference S, and sometime in the future I got like a raise or something, it would still kind of flow back to this time, and they would still be positive, and I might do a great presentation again someday. Yeah, and yeah. Next phase. And why the PPS clipping is so important. So there are typically the policy gradient updates can be kind of unstable. So a single large reward could kind of mess with the early other phases in the gameplay. So for example, if I had this example where an agent finally kills a boss and gets a huge reward. Then the probability of the killing blow will grow to, say, 1 or something close to 1. But also it will change the policy during the earlier phases of the game. For example, if there was a right path and a left path, right path is the correct one that leads to the boss, it might actually change so that it will take the left path and run into a pit of lava or whatever, or not even get outside of the first room. So PPO solution is to clip the loss function. So we have the model parameters and whatever happened and the reward, and we compute the gradient, but we have no information about how much the gradient will actually change the policy ahead of time. We only have it after we did the update. And if the update is much bigger, or bigger than some specific amount than during the rollout, then we actually zero the gradient and say that, okay, no more updates in this direction. And that works really well. And then more about this training strategy. So there's a separate pre-training phase where the model is trained on all maps with random gear. It's ready to run for as long as necessary. And then fine-tuning phase during the actual balancing runs, where we run the training, one training instance per scene. And that cuts down the training time to maybe 10-20% compared to if everything was trained from scratch all the time. And then during the fine-tuning phase, or the balancing run phase, there's also a separate gear optimization. So all the agents have 12 possible gears. Slot 1 is a weapon, slot 2 to 4 is a gadget, and then the gizmos and power stones and whatnot. And they are just categorical variables. So there's a simple genetic algorithm. Basically, let the agents play, rank them by, for example, total reward, then keep maybe 10% or 50% of the best ones. Everybody else dies. And then there's basically sexual reproduction between the top performers, and they will make babies by crossover mechanism, select a part of genes from one parent and rest from the other, combine them, and then a random mutation. It's all kind of simple, just NumPy array manipulation. Yeah, and the core challenge, as usual in reinforcement learning, is the credit assignment problem. So if there's like a 5-minute battle, 5 minutes is a short time like compared to human credit assignment stuff. But if you only get a reward for completing dungeon, how does the agent know which of the actions actually were helpful? Or how would the agent even like reach the end stage if there's no rewards? So, and a kind of a no-brainer solution is reward shaping. So we have access to the full game state, so we can define any kind of rewards we want. So this is really useful. So early stages of the game we give this simplest possible rewards, like staying alive, just running from the monsters. Then they accidentally maybe hit the monster and get a higher reward out of that and start to prefer the hitting, and even higher reward for killing, and kind of move on up this hierarchical ladder. Hitting a boss even higher, killing a boss even higher, completing the dungeon, you get like a huge reward, and eventually they should then focus on fast completion of the game. So it works great. This kind of hierarchy, different phases of the game. If the reward scales are just right. So in practice, what this means that you have to do quite a bit of reward engineering, like setting these different levels of the rewards. Because again, you can't really tell ahead of time like how much you're going to, or the agents are going to collect different rewards. even if the like monster hitting reward was low, maybe there's lots of monsters, so they would prefer just hit the monsters instead of going to the end. Another problem that was kind of occurred last spring. So there was this new gear in chapter 2 called squid blades, which work so that in a way that if the players don't attack for some number of seconds, maybe 5 or 10 or something like that, the player turns invisible. The monsters don't see the player. So the optimal kind of more or less obvious human strategy would then be if all the 4 players choose the squid blades and then just sneak through all the monsters and go to the boss and kill the boss immediately. But the reinforcement agents kind of failed that quite badly. So they basically just couldn't resist killing the monsters on the way. Didn't really figure out this strategy at all. Yeah, shit, that happened. So yeah, maybe you could do some more reward engineering here or something, but maybe it's also like an opportunity to try something else. So as a recap, so balancing lots of rewards, difficult, time-consuming, and the agent might learn to farm these auxiliary early-stage rewards instead of trying to go to the end. So the ideal solution would be a minimal reward signal, just maybe for the completion or fast completion of the game, and some exploration mechanism. So I did an experiment. So I took a pre-trained model, trained with all the rewards, and then during fine-tuning just enabled the boss damage, boss kill reward, and the staying alive reward. And so yeah, so kind of worked as intended. So this is actually how the squid blades work. They will turn invisible now, okay, and then they go past the monsters. So it works. They learned that, but it did really hurt the training in general. The training became much more unstable, and in some cases, the agents just can't find their way to the end. So the early stage rewards and the reward hierarchy is really important. But okay, can we maybe figure out some kind of like an exploration solution here instead of these early stage rewards? Just being able to reduce the number of rewards would be really nice. So how do we encourage exploration? So one kind of like a popular or method that's been discussed in, well, whatever, literature and whatnot, is curiosity. So how do we define an agent to be curious and try different things? Some kind of really common low-level techniques is just adding an entropy bonus. So in the loss that we're optimizing, add on so more entropy bonus that will kind of encourage slightly higher entropy than just collapse into zero entropy, like probability 1 actions. That works kind of well for like a general regularizer or whatever. And another like really simple one is pseudo counts or just counts in general. So penalizing the agent for visiting states that it has seen many times, given a negative rewards for states that it has visited. That kind of works, but if the number of states is high or if there's continuous states, then how do you do that? So my one kind of early solution was what I call boredom paint. So basically, remember the tile map in the earlier slide. So the agent will kind of insert lots of this boredom paint on the tile that it's standing on and less like near the corners, and then it will also observe this kind of border on the map. And that works really well for geographic exploration. But it's kind of like, I mean, you need an extra camera channel that it will observe, and it's kind of like how do you implement that? It runs fine on GPU, but it's kind of a little bit complicated. Okay, and then well, how about some literature? So a general word of warning for like a machine learning practitioner: if you're trying to implement papers, the odds are that it's not going to work, or that even that the kind of statements in the paper were kind of misleading or exaggerated. That often happens. So you have to be kind of quite critical of what you read. But anyway, many of the exploration methods can be expressed as state entropy maximization. There's a reference to a nice paper by Peter Abel's team. So you pass observations through an encoder. It could be similar encoder as in the actual agent architecture, or even the same one. And then use a k-nearest neighbor estimator to estimate the entropy of the outputs of the encoder over the rollout. And if the estimated entropy is high, you give a big bonus reward. If it's low, no reward. So it's kind of pseudo counting, but in this continuous abstract latent state space, the encoder outputs. Se Kozachenko learning, that sounds kind of scary, but it's actually kind of simple. Here's a visualization. So on the left-hand side, there's a low entropy state trajectory, and on the right-hand side, a high entropy one. So you could think of the axis as just position, coordinates x and y. So then the agent starts from there and does a random walk, ends up at the red triangle. If you took the k nearest neighbors from the triangle to the other points, okay, clearly they are close by, so you get shorter distances on average. So the state estimated entropy is low, and the opposite in the high entropy case, the red triangle is far away, walking almost straight path. So the entropy would be high in this case. Yeah, so okay, so trajectories or points don't have entropy, but if you want, you can think of it like these are samples drawn from a low state entropy distribution and so on. Okay, so experiments. So kind of a nice baseline is to exactly use the positions. So during rollout, record all the positions, and then you can after the rollout you can find the k-nearest neighbors quickly, or run on a GPU. Touch .topk function does that quickly on a GPU, and assign the rewards based on the k-nearest neighbor distances. And this works nicely. So we can use it. I'm now using it to replace the kind of complicated boredom thing. Yeah, nice, works. So that's a success, a nice baseline. But then using the actual k-nearest neighbor latents out of this, the extra encoder or the agent's own encoder, kind of same as before, except I was also using this inverse dynamics module. I was also testing without that. So basically the idea is that you take two consecutive states, S at t and S at t plus 1, and try to predict the action that took the agent from st to st plus 1. The idea is that that will basically filter out all kinds of irrelevant information from the encoder, like random noise or whatever. And otherwise, same as before. Well, okay, well, this isn't quite work. So I actually tried many different encoder outputs, but I was still trying this last week, but couldn't really get it working. But it's still kind of ongoing. And I think the reason is probably the unstructured observations. Like this typically works quite well with pixel data. When you kind of move around, you get actually different looking things. But instead here, you get like they learn to optimize this reward, this intrinsic reward, but it just doesn't correlate with the actual rewards like boss damage reward and so on. So yeah, not sure if it can work here. Okay, yeah, so this is the end. Recap. So we use the reinforcement for the game balancing. Word shaping is a challenge. Yeah, it would be nice to have like a go-to solution that you can kind of drop in, replace with any game. This is still quite far off, if not even possible. The position-based KN exploration works. Maybe that's good enough. But anyway, the exploration journey is kind of still ongoing. So thank you. Time for questions.
Thank you for the nice talk. I have just one question. I'm trying to understand the K nearest neighbor exploration position based. So did you look for like bosses or other bots nearby the agent when you're doing the exploration? Because wouldn't you want them to have like high rewards if they kill someone near that area? But from that graph, it was like one direction, and the high entropy would be if they are further away from the.
Well, I'm not sure if I'm following that thought, but basically the idea of the exploration is to kind of keep it separate from the other rewards or any kind of like a explicit monster positions or anything. So basically the idea is to kind of go away from the previous stage that the agent has explored. I'm not sure if I understood the question.
So like there are bosses at every location, right?
Yeah, typically.
Yeah. And you don't want the agent to do random walk. You want it to go in a certain direction. So when it's doing the KNN exploration, is it looking for other like bosses or agents? I mean, I'm just trying to understand.
No, it's yeah. So the idea is not to give like explicit information about the boss, but just to how should I explain it? I guess that might be a too difficult question.
Sorry.
Maybe we can discuss it later.
Yeah, sorry. I am not an expert in this.
Yeah, okay.
Hi, thanks for the talk. So what kind of metric do you use for kind of the balance aspect? How do you know it's like well balanced? Like it's not too difficult for the agents or not too easy for the agents. So let's like, how does the agent map to a human?
Yeah, okay, that's a good question. So I don't. Basically, that's the game designers kind of design the levels based on how they would want the players to behave there. And then I just basically run these runs and return the results on like a spreadsheet that's reporting like the average completion rate and stuff like that. So if the completion rate is 100% all the time, then it's too easy. If it's 0, then it's too hard in general. But the game designers are kind of responsible for kind of drawing the final conclusion.
Yeah, I'm just because that's like the like completion percentage is like it depends on how long you run the agent, right?
Yeah.
They might be just very good, much better than the average player or something.
Yeah, definitely. There's lots of numbers also, like this actual speed of completion also and stuff like that.
Makes sense.
Thanks.
I was here first.
But in continuation of that, how would you approach the problem of simulating users with different skills? So like agents of different capacity. Would you just like limit the training time, or are there any tricks other than that you would differentiate the bots by the sort of proximity of the user skill?
Yeah, so I haven't really thought about that a lot. There's been quite a bit of discussion about that. So do you mean like how to make them more human-like?
No. More in terms of the how proficient are they at the game? Like the bot that sucks at the game, the bot that is like an average player, and the bot that is like a pro.
Yeah, I'm not sure. So I don't think we have like lots of data compare. I mean that we use to compare to the bots to actual players. So yeah, so we don't really do that a lot. Not sure if you're happy with that.
Yeah. I think one of the innovations in the Alpha Star from DeepMind, which plays StarCraft 2, so not the same game, but I think they try to mimic human players to get more of this exploration, because of course there are human players with lots of experience. I don't know if you have the same.
Well, PvP games are kind of different because one party will always win. So it's maybe like a little bit different case, but still, I'm not still kind of sure if I really got there.
Okay, let's see if I still remember it. Did you ever find exploits, like game mechanic, that you decided like this is not really a problem, this is only something a bot could do? Or if you didn't, is that like already solved by your like simulation environment that bots can't do things that are actually superhuman?
I might have some problems with my brain, but also I have difficulties understanding the question. Can you maybe rephrase?
Yeah, can bots like act actually superhuman? Would be like the simple version of that question. Like in your simulation environment, can they act faster than a human could possibly react?
Well, the reaction time is limited to 250 milliseconds, so 4 actions per second. So that's kind of hard coded. So they can't be like super fast. And in other regards, also the gameplay is kind of not that complicated. So you can't really do any kind of like insane stunts in the game. So they aren't really that superhuman.
Hello. So one question about this reward shaping thing. So I understood that it is kind of like one part of it, at least, is about setting the correct weights for different kind of things you do.
Yeah.
So have you considered using reinforcement learning for setting those weights?
No, but yeah, might make sense. Then again, I would imagine that would probably increase the training time a lot. But yeah, too many things to do and too little time. Too few people.
One more question, because you're in the middle of pizza.
Yeah, related to the question about different player levels, are you trying to model players who are paying more or less money into the game? Because that's probably relevant to the bottom line.
Yeah, no, not currently. So I'm not really currently focusing on the implementing bots specifically for the game, just for the balancing. But maybe someday. I don't know.
Great talk.
Yeah, thank you.